Thank you for tuning in today. I've decided to tackle the very important and apparently simplistic but sometimes non-intuitive topic of solubility. And I'd like to take you through this concept sequentially, all the way from GCSE to a more synoptic approach that's applied at A levels, sixth form HNC, HND, and upwards. By starting at the concepts that are offered to us at GCSE and how a synoptic approach is developed as we go upwards, sixth form HNC, we have to see how solubility and solubility product links to chapters such as enthalpy, thermodynamics, and reaction kinetics. And how its numerical calculations are carried out in molar ratio proportionation calculations. So the first thing I'd like to start off with is the solute. Solute is the solid, either salt or element or compound being dissolved in its relevant solvent. So if it's an organic compound, then it ought to be dissolved in methane or cyclopropane or what have you. And if it's an ionic electrovalent solid, then it ought to be dissolved into water so that an ionic electrovalent solution would form. So solute is salt or element or compound measured in grams. Yes. Now you can calculate mole as well, which would be mole equals mass over atomic mass or relative molecular mass, depending on whether it's an element or a compound or a salt. So if it's a salt or compound, it'll be molecular mass, and if it's an element, solid element being dissolved into what, then it would be relative atomic mass. For example, sodium solid being dissolved into water, it'll be a dynamic equilibrium back and forth. Le-Chatelier's principle applicable here, and it would form NaOH, sodium hydroxide, aqueous, highly alkaline solution with hydrogen gas being given off. In the past, they used to denote this upward arrow, but it's no longer applicable. You just use the symbol G, and you'll have to balance it out. So it'll be so if it's so half a mole of 1 and 2, so or just half a mole, which is not correct. I mean, I don't go with fractional molar because there's no such thing as half a mole. Well, I mean, it'll be half the Avogadro number of particles, but it's much easier to just do 2, 2, 2, and 1. So integral value would be 2 Na plus 2 H2O plus 2 NaOH. And then now the other thing I'd like to say, that the other part is solvent. Solvent is either a polar or a non-polar solvent, and it is what's used to dissolve a salt or an element or a compound. So it's measured in milliliters, mm cubed, decimeters cubed, and liters, and so that's that. And so then solute plus solution solvent forms a solution under dynamic equilibrium, and that'll be the equation for it would be solution divided by solvent. The solid would not be part of the dynamic equilibrium, and then it's very similar to P1 plus P2 and then R, and it can be R1 and R2 and R3. In most cases just R1, and sometimes it's R1 and R2, and very rarely it's R1, R2, and R3. You could also call it R and R prime and R prime prime. So that said, a solvent and solution are mixed together. If they are compatible, then they form a solution. But what you need to realize that it directly links to thermodynamics because of U, Q, and W. So this is work done, and this is the heat energy, dq over dt, where that's being supplied. Or if it's not being supplied, in solid, in case of solubility, I should have told you that it's all about dissolving maximal amount of solute in the solvent at incremental temperatures, and then once you stop it, then the temperature drops and things begin to crystallize and recrystallize. I'm not going there yet, but so, and then the dq dt makes the work done, and then U, which is internal energy, it denotes the average kinetic energy of the solvent and solute and solution, and how particles are vibrating, translating, and rotating. Because there are three types of internal energy, which is rotational, vibrational, translational energy, internal energy, and they rotate about the axis, vibrate along the lines, and translate up and down the axes. So that's how the energy, average kinetic energy, is expressed, and potential energy is also expressed. So internal energy, this is internal energy, and it continues to increase per unit time, because heat is being supplied and so work is being done. And sometimes the work, solute does work, and sometimes solvent does work on solute, and sometimes both is happening. But you have to simplify it and make it, because it's so multifactorial, you have to sort of assume a few things and then just try to uniform it. So now let me introduce you the topic of solubility in more a calculational format. So solubility, the science of solubility, is the incremental solubilization of unit mass of solute per unit volume of solvent as a function of time at upward and at positive or negative temperatures. Negative temperature differential. Very technical, very posh words, but this is how you'd write in the exam. So the solubility is the incremental solubilization. The process of solubility, calculation, measurement, and quantification, is the incremental solubilization of unit mass of solute per unit volume of solvent as a function of time at positive or negative temperature differential. Now what's happening is that you're adding grams of solute per unit volume of solvent, and it's taking time and Q, and so it's dq over dt. One thing I'd like to clarify further is that this won't be expressed in grams, it'll be expressed, it should be technically be expressed in moles, so it'll be moles per liter or moles per dm cubed, for calculation purposes. But we don't get to that until we do solubility product, which is the A-level concept. So at GCSE, the calculational graphical analysis would require you to have grams per grams or grams per liter at max. So what's happening is that heat energy is being introduced into the system per unit time, dq over dt, and we know that heat energy is mc theta t. So all of it is linked, interlinked, and cross-linked. So this is what the equation for heat induction into the system is. So heat is being introduced into the system, and work is being done upon solvent, and solvent does work on solute to enforce incorporation. So enforce facilitated not facilitated as in facilitated diffusion, because that's a passive process. Yeah, you might roast me on this, the use of word of facilitated, but it's being facilitated by heat energy, so it's not passive. So enforce non-passive, or you could just say active here, active / non-passive facilitated incorporation of solute to enforce its active non-passive facilitated incorporation. So that's that. Now let me repeat myself. The incremental solubilization of unit mass of solute per unit volume of solvent as a function of time at positive or negative temperature differential is known as the process of solubility. And there's the mass of solute involved, there's the volume of solvent, there's the time in seconds, there's heat energy in joules, joule meter, and then energy induction dq over dt equals mc delta t in kelvins, and then work is being done upon the solvent, and solvent does work on solute to enforce its active non-passive facilitated incorporation. So that's that. And so the whole process of solubilization is very, very nice, and very entertaining to look at. It's very nice and pleasing to the mind. It's very intuitive. It's not non-intuitive like simple harmonic motion or the proofs of Henry or Hall effect. So please bear with me. Now, whilst all of this is happening, whilst you have, sorry, I apologize, you have this anti-bumping granules at the bottom to prevent, and then you have the Bunsen burner, and then you're solubilizing, you're adding solute. I'll give you specific examples later. So, and then you've got the solvent here, and you're continuing to increase the temperature. Now, what's happening is that along with heat induction, dq over dt equals mc delta t, you're also coming across evaporation, boiling, because you're boiling the liquid. So boiling point is the equation of when STP, standard temperature pressure, equates atmospheric pressure. That's when boiling takes place. And boiling is taking place, so there's a loss of mass of solvent per unit time, and there's a downward, so I'm going to denote it as a negative. So m solvent negative per unit time, dm over dt, and then there's the incremental increment of solute per unit time, so that's positive m solute per unit time, so dm over dt. So you can see that now you have to keep the temperature so as to prevent boiling, but ensure that the temperature increases, and you are not inducing boiling, but you're continuing to increase the temperature high enough so that it continues to facilitate the active incorporation of solute with the help of hydration enthalpy. And look, now we're getting to the point where saturation, supersaturation will come into play, and we've already dealt with thermodynamics aspect of it, which is QW and U. And W, just for your information, is pressure delta V. So volume change times the pressure. So that's your work done. And your Q is dq over dt equals mc delta t. Now that's that. Whilst all of this is happening, you have enthalpy of hydration, enthalpy of solution that are also acting in there And I'm not going to go to Born-Haber cycle or the other one, but what I will, Hess's law. I'm not going to go into that because it doesn't apply here, because that's about burning and evaporation and sublimation. But here you can see that enthalpy of hydration is involved in opening up the water molecules to incorporate more and more solute till they reach a saturation point. Now, saturation point is negotiable, but not. But supersaturation point is non-negotiable, past which no solute can be incorporated actively at that or incremental temperatures, because the capacity of water to incorporate and absorb and assimilate and process the solute whilst remaining a clear solution has passed its supersaturation point. It can't take anymore. It's going to turn cloudy, ultra cloudy, and then when the temperature begins to decrease as a function of time, which is dt over dt, which is Kelvin per seconds, crystallization and would take place, and then recrystallization would take place when the temperature drops further down. And so that's the theoretical approach to understanding the chapter of solubility. It's now I'm going to make it a bit graphical. So now now what you need to do is to realize that the graphs of solubility, and again, Sykes, Ramsden, these are leading calculational chemistry books, and they have a very comprehensive chapter on solubility calculations. And so they would tell you that they put I think it's temperature here, or let me just double check. So this is Sykes chemistry calculations for GCSE, IGCSE, and higher GCSEs. It's a legendary book. Has helped me quite a lot. I still use it. So in that, solubility is yes, molten solutions, and that's page number 47. Solubility of solids, yes. So, and they make it slightly more technical, lab-based. You have to delete the massive dish, massive solution from the massive solution and solute. So that I didn't mention, but that's you have to do it when you're working in a lab. So the graph, I'm going to get to the graph. You can now, there's many kinds of graphs you can draw. The kind of graph they're drawing is temperature on the x-axis and solubility of the salt per 100 grams of water on the y-axis. So, but for beginners, you could have three graphs. You could have you could just have a temperature here, sorry, Kelvin, not degrees Celsius, but Kelvin, and then you could have mass of solute, and then the curve would be like this, because it would begin to plateau here because of all the limiting factors. The limiting factors would begin to influence the solution solubilization, as I explained previously. So sorry, excuse me. Where's that? Where's 47? Yeah, so they've been putting temperature here, and they've been combining mass of solute dissolving in 100 grams of water on the y-axis, which I sort of don't agree with. Not for normal new students. I would do two graphs. One graph would be mass of solvent, mass of solvent, and mass of solute. And then I would draw a graph here, and then I would draw a graph of mass of solvent versus temperature, and then you'd be able to clarify your understanding. Then I'd move to this kind of graph, which assumes you have an understanding of this and this, but most students don't, and they get confused. And so there's a thing called molality. Molality is grams of it's grams per liter, whereas molarity is moles per liter or dm cubed. So grams per dm cubed or moles per dm cubed. So that's becoming non-existent, more and more non-existent, because it's an older concept. This is the new current concept and is in use, and it has replaced molality ever since. So coming back to my aspect of solubility, now what you need to realize is that from these questions you're required to find out at what temperature, how much dissolved at what temperature, and you're supposed to just interpolate, extrapolate, and calculate the rate of change. Talk about limiting factors. Nature of solutes and solvents. So this is what they'll ask you out of it, and then we'll do one question, and that'll give you an understanding of how things are. So using the solubility curve for potassium nitrate, let me first ionize potassium nitrate, adding it to water. Sorry, I'm not adding the state symbols. That'll be K plus H plus OH plus NO3. Yay! So 1, 2, 3, 4. This is what we have available, and this is the, you can make a conjugate acid, conjugate base out of it. So that's one form of resolving the equation. The other form is KNO3 plus H2O and KOH plus HNO3. So you can see that there's a weak acid and weak base here, and this would be a conjugate acid and base, and this would be a conjugate acid and base, because there'll also be a formation of hydroxonium ions, which are a popular entity, but they're not discussed very much. Hydroxonium ions. So yeah, so it asks you, so we need to keep an eye on this curve, this one here, and so we can see that in this particular curve, it's overall it's 100, and they have a control in here, which is sodium chloride, and they've added the potassium nitrate. Now it says using the solubility curve on potassium nitrate in figure 5.4, this one, what mass of potassium nitrate can be dissolved in 50 gram of water at 20 degrees Celsius, which is 293 kelvins. So first we have to look at 50 grams of water. So 50 grams of water would be round about overall dissolution for so we have to go at 100 first. So this is 100 gram of water overall, and we were able to dissolve around about 240 grams in 100 grams of water till 100 degrees. Now here it's saying, it's asking it for 20 degrees. So for 20 degrees we have to look at how much has been dissolved, and then we have to halve it, I suppose. So that'll be, it's very vague interpolation. So if we interpolate it, it comes out around about 38, and then when you divide 38 by half, when you halve 38 you get 19. The book says 16, but I disagree, because it doesn't look like 16, it looks like 38 to me. Divided by 2, that's 19. The next question is, what volume of water is needed to dissolve 96 grams of potassium nitrate at 20 degrees? 96 grams, that would be quite unitary. So at 20 degrees, equals 293 Kelvin. You were able to dissolve 38 grams per 100 gram, and it's asking you how much mass of water would you require to dissolve 96. So that'll be, so if it's 38 grams for 100 grams, then for 96 grams would be grams, and that'll be 100 grams times 96 grams divided by 38 grams equals X grams. So that's that's 252 according to my calculation. It shouldn't be 300 because that's way too simple. That's for GCSE level. So that'll be 252.63 grams. That's what I'd write in the exam. 252.3, not 300, because I disagree with the interpolation. It should be 38 here, not 32. Now the next question is at the same, so at 20, again, the same temperature. They should have varied it a little bit to make it difficult. At 20 degrees, the mass of nitrate dissolves around 16. So is that true? At 20 degrees, it's able to dissolve 19 grams. So the mass crystallized would be 31 grams. So if so at 20 degrees, the mass of potassium nitrate dissolved in 50 grams of water is 19. Because in 100 grams it was 38, it'll be 19 in 50 grams, and so the mass crystallized would be 34 grams, which doesn't make any sense. If it's dissolving, it seems a bit non-intuitive, which is why I marked it, because it shouldn't come out as 34, which means all of it is coming out, which doesn't make any. So now, if 38 grams of 19 grams is dissolving at 50, and this is what you dissolved, why would 31 grams come out? That's a bit, that's for another video. Yeah, so moving on, I'd like to make a few things clear. When you're forming a solution, you have to talk about molarity, not molality. Molality is an outdated concept. You have to measure, and you have to measure the mass, and then deduct the mass of flask, mass of and the dish from the or you could just zero it, which is not very accurate sometimes, because there's always a negative measurement, negative differential in the gravimeter of the machine, and there's always an inherent systematic error. So I think deleting the amount of the mass of the dish and flask would be much better. Then you stir it, and then you make a standard solution, and then you wash the beaker, and then and then you make a standard solution out of it. And then also you could use now. Okay, so now I'll do another question for you that'll give you an understanding of how things should be here. This question talks about what's the concentration of a solution of sodium hydroxide that's made by dissolving 20 grams of solid in water and making the volume up to 250 centimeters cubed. So we know that N equals CV, which is number of moles equals concentration times volume. So and number of moles is mass over molecular mass or atomic mass, and in this case it'll be sodium hydroxide plus H2O. Ionizing the dynamic equilibrium, that'll be sodium OH H plus OH. So we can see already it's a highly alkaline solution because you've got two OH and one H only. So you know they're outnumbering by a proportion of 2, and we'll later check that out in solubility product when we do it. Now, the molecular mass of sodium hydroxide is 23.5 grams of sodium plus 16 grams of oxygen plus grams per mole and grams per mole plus hydrogen 1 grams per mole. That'll give you 39.5 and 40.5 grams per mole, 17 and 40, yeah. And then so you're dissolving 20, so that's half a mole almost. So 20 grams divided by 40.5 grams per mole. So gram cancels and mole comes on top, so that'll be 0.5 or approximately. Not approximate sign and then mole. And then you have to do a solution, which would be molarity, which would be number of moles, N1 C1 over, so C equals N over V. So that'll be 0.5 mole divided by 250 cm cubed divided by 1000 cm cubed. That'll be 0.5, and then so for that'll be 2 moles per dm cubed. 2 moles per dm cubed. So it'll be 2 moles per dm cubed. So the formulae I used were N equals CV. And then I used C equals N over V. I used N equals M over molecular mass. So these are the 3 formulae I used to find out the answer, and it was quite easy. I'll give you more examples as to now. One of the what you need to realize is that different families of compounds have varying solubility ratios based on their electrovalence, based on their polarity and polar non-polar nature, based on the solvents. And I mean, you can't expect sodium to dissolve in oil for obvious reasons, viscosity and polarity and whatnot. So what now will happen is that you have carbonates, bicarbonates, hydrides, hydroxides, carbonates, bicarbonates, hydrides, hydroxides, sulfates, nitrates, nitrates, and then halides like iodide, bromide, fluoride. All of it comes in the halides, and then carbonate, bicarbonate, hydrides, hydroxides, sulfates, nitrates, and halides. And then you have what's the other compound family? Oxides. Sorry, I missed oxides. and then carbides. Now we're delving into silicates and let's not go there, because that's going to take us into a new realm of chemical compounds, which are giant molecular, giant covalent lattices. Solubility occurs most efficiently between water and ionic compounds. And then there are varying degrees of solubilization ratios between non-polar solvents and molecular compounds. So you could get lead carbonate, you can get copper hydride, you could get copper hydroxide, you could get potassium sulfate, magnesium nitrate, barium chloride, barium fluoride, barium iodide, and then sodium carbide, and all sorts of oxides of group 1 and group 2, and they'll dissolve into water at varying rates depending on their electronegativity, ionic charge, nuclear charge, and I shouldn't talk about individual aspects such as nuclear radius and ionic radius, and but that also matters. So ionic radius, and so on and so forth. So first, ionization energy. Second, ionization energy, periodicity, and group group characteristics. So all of these things, then solubility leads into titrations, indicators, and indicators have their own solubility ratios as well. Solubility like Hi plus H2O, and then it would be H3O plus I, and then that's how the indicator would dissolve Congo blue and phenolphthalein, and either they give you a different degree of sensitivity to various pH ranges. We all know about that, and so this is how things are. And now I'm going to, I'll do a few ionizations for you. And, in this particular example, like some carbonates and nitrates are very, very difficult to dissolute because of their, ultra strong, hypercoulombic electrovalent structure, and very difficult to break them apart. And even in electrolysis, electrochemistry, some like sulfates, carbonates, and nitrates, they don't come apart even under electrical influence, electrical energy. They don't come apart. That's how strong they are. And it takes quite a lot to dissolve carbonates and nitrates. And sometimes it takes warm water, excessively high temperatures, to dissolve nitrates and carbonates, and it can be very, very difficult. And so the easiest to dissolve are perhaps sometimes sulfates, bicarbonates, halides. They're very easy to dissolve. And then most solubility precipitation, double precipitation reactions take place with the help of halides, because they're very quick to give you results. And you can have double precipitation where you have for example, two salts out competing each other, so Becquerel 2 and then KNO3, giving you BNO3 plus 2 KCl, and then I'll have to, obviously sort this out here. And yeah, so and then this one would, one of them would be a solid here, and that one would turn liquid, and the other one would precipitate out. And and so something, precipitation, sorry, double precipitation, and then displacement and double displacement. That's how things are panning out. And then Solubilities chapter also links you to the test for ions and gases, and also links the a chapter of analytical chemistry, where you test for different gases and ions. So that's that. And so I think I'll be concluding the idea of solubility. And before I do, I'd just like to clarify that you do use N equals C over V. You use C1 V1 equals C2 V2. You also use C1 V1 over N1 equals C2 V2 over N2. You also use N equals M over MR. So you use all of these formulae to develop an idea of how things are. And then in the previous, I spoke of dq over dt equals mc delta t, and then p1 p2, so that's the substrate giving you the product. So E1 plus so in enzymatics Michaelis-Menten equations. So here in chemistry, it's reactant 1 plus reactant 2, giving you a product, a range of products, P1, P2, and sometimes P3. Or it can be enzyme plus substrate, enzyme substrate complex, and then giving you the product plus enzyme, because the enzyme comes off. And that form, that's part of Michaelis-Menten. And then it can be so the equilibrium equation would only consider solution format or solutes or solvents. It wouldn't consider the solid part. So it would be P1 concentration, P2 concentration, so X, Y, Z, and the Z would be this part. If it's 3 or 5 or whatever, that becomes the multiple becomes the exponent. So if you have Becquerel 2 plus H2O, which is pure liquid, so it won't be part of the equation. So that'll be, just eliminate that for now, and then just focus on the salt. So if you dissolute it, aqueous, the equation would be Cl2 squared and barium singular divided by Becquerel 2. Yes, it's a solid, it's not supposed to be part of it, but here in this case it would be. You can't take pure liquid. So this is the multiple. The multiple becomes the exponent. 2 here becomes squared. Now let me jump over to, so now I please, if you want to get a summary or gist of this video, please rewind it to the beginning where I was talking about dq over dt and the work being done upon the solvent to incorporate as much solute. So the solvent does, so heat, the Bunsen burner does work on solvent, and the solvent does work on solute under the guise of enthalpy of hydration, enthalpy of solution, and does work on it to incorporate as much solute till the saturation point, which is negotiable, but supersaturation point, which is not non-negotiable. And then things begin to clarify after that. And then once temperature drops, for every decrease of temperature, you will feel you will feel the effects in form of crystallization, recrystallization, just as you do in displacement, double displacement, precipitation, and double displacement reactions. It can be quantized, with U, Q, and W, and dQ over dt equals mc delta T. The molar equations I just mentioned, N equals C over V, C1V1 equals C2V2, and then C1V1 over N1 equals C2V2 over N2, and then N equals M over molecular mass, and that's how things will be. Now, that all links onto solubility product. The solubility product, again, this is molality. This is what I was talking about. This is molality. So this is molality. The solubility of calcium sulfate at 298 Kelvin is calculate solubility product at this temperature. Now, this is a bit tricky because it's asking you to convert grams per dm cubed into moles per dm cubed. You have to do it. You can't do grams per dm cubed. It's not going to make any sense. So I'll solve, I'll solve all the problems. Bear with me, please. So this is where the idea of solubility in GCSE links to solubility product at A levels. Okay, so this chapter investigates the three sorts of equilibria, dynamic equilibria calculations, which does not fit easily into the places in the book. There isn't anything difficult in terms of the maths. So solubility products are included because it's part of reaction kinetics, and a saturated solution is one which contains maximum amount of dissolved solute at a particular temperature tier, and it can be negotiated, in my opinion, in my observational analysis, and in the presence, and there is a presence of an undissolved solid which may appear as cloudiness in the liquid, and so what it's trying to say is a saturated solution is one which contains the maximum amount of dissolved solid at a particular temperature tier in the presence of undissolved solid. In the absence of undissolved solid, some substances can form unstable supersaturated solutions. As soon as you add some solid to these, all the excess dissolved material precipitates out. So there's quite a lot of Lee Chatelier's involved here for those who studied it at GCSE. So, and then we can take different kinds of salts, lead sulfate here. We can ionize it, and then when you ionize it, you can see that lead sulfate both are bivalent and they are equimolar in their proportionation distribution. So they wouldn't have any exponent here. They would just be mono-exponential, and then you can multiply the concentrations. And if, for example, if the concentration was 0.95 mole per dm cubed, you just multiply 0.95 with 0.95 and 0.095 again, so 0.095 squared, and it will give you the answer. Or if it was 1 mole per dm cubed, if the lead solution was 1 mole per dm cubed, it would be 1 mole per dm cubed for lead, and the same for sulfate ions, and then you'd square it and you'd get 1 mole per dm cubed in solubility product. But if it was 0.5 for lead sulfate, it'll be 0.5 here, 0.5 here, and then you'd multiply it, you'd get 0.25 moles per dm cubed, moles squared per dm cubed 6. So it'll be because you're multiplying it, moles per dm cubed, moles per dm cubed, it'll be m squared, which would be moles squared plus dm hextupled. So it'll be moles per dm this. And then you have salts that are disproportionate in the ionic product. So you can have aluminium phosphate, which is the best example. You can have aluminium phosphate. I'm not going to add aluminium phosphate, which is, sorry, aluminium phosphate, which would then dissociate disproportionately because they are disproportionate. One's bivalent, or the other one's trivalent, so their distribution would not be equimolar. It would be anisotropic. So it would be 2Al3 plus 3PO4 negative 2. So bivalent and trivalent. And so if we had let's just say, let's not complicate it, 1 moles per dm cubed here, it would be 2 moles of aluminium ions in the solution when it dissociates disproportionately because of bivalency and trivalency, and it's not equimolar. And then it would be 3 moles for the phosphate, and then we multiply it, it would be the multiple would become exponent, and then it would be so 2 molars squared, sorry, my brackets, and then 3 moles cubed. So that'll be, no, sorry, there's no multiplication, there's multiplication, there's no addition, I apologize. And then it'll be 4 moles per 27 moles, sorry, there's no addition, 27 moles, and then you multiply it, it would be 58, 54, 108, 100, so 27, 27, 54, 54, 108 molarity squared, which would be 108 moles squared per dm6 minus 6. It's not a square, so you don't need to underroot it. That'll be your answer. You can see that it's the best example for a disproportionate anisotropic distribution, ionic, which is not equimolar. And the other example I'd give you from the book is a very good one, bismuth sulfide. Bismuth sulfide. So it'll be bismuth 2 and sulfur 3. So basically bismuth is trivalent, sulfur is divalent, and it would dissociate in a non-equimolar proportionation, which would be 2 moles of bismuth, trivalent bismuth, and 1 mole of trivalent, 3 moles of trivalent sulfide. And so the book says, well, the book didn't say it. So if I say, let's just say it had a molarity of 1 mole per dm cubed in a standard solution. Bismuth would be 2 moles, and sulfide would be 3 moles. And so when you're about to take this solubility product, it would be bismuth 3 positive squared, and sulfide 2 negative cubed, 2 squared, 3 molar cubed, so that'll be 4 moles, and then 9 mole, 27 mole again. So it's the same answer. So that'll be 108. Hang on, in this case the molarity would be mole squared. So that's with the square, yeah, so that'll be 5. So that'll be moles 5 plus dm cubed minus 15. So I rectify my error here. It'll be moles 5 and dm cubed minus 15, because it's mole squared here and cubed here. So the powers when multiplying would add, and it would be more 5. So again, you can see that it's a very this is a very interesting, entertaining kind of calculation of all the reaction kinetics components. And I'll do a clean example again for you. The clean example would be, let's say, magnesium phosphate. Let's just say that magnesium phosphate, Mg. No, that's not magnesium sulfate. No, we need to pick something that's trivalent. So magnesium sulfide would dissociate in a non-equimolar fashion to 3Mg plus 2 and a 2S minus S3 minus. Now let's just say if it were a 1 mole standard solution in a flask, magnesium ions would be 3 moles and sulfide ions would be 2 moles. Now in solubility product calculation, it would be magnesium divalent ionic cubed multiplied by sulfide trivalent squared. So we can already see that the units would be pentupled. So it'll be 3 mole per dm cubed multiplied by 2 moles per dm cubed squared, and that'll be 27 moles cubed times 4 moles squared, and that'll be 108 mole pentupled, K subscript SP, K subscript SP, K subscript SP, and the units would be moles pentuple divided by dm cubed 15 to the power 15. That's what these m to the power 5 means. This is what the m to the power 5 power means. So you can see the sequence of calculation so it's magnesium sulfide. Look, I'm not going into detail whether it dissolves perfectly into whatever, assuming for this particular example that it dissolved perfectly into water in an electrovalent fashion, and we made a standard solution out of it, which was 1 mole per dm cubed. So out of that 1 mole per dm cubed, 3 moles per dm cubed was the concentration for magnesium ions, and 2 moles per dm cubed for the sulfide ions. And it seems very, very non-intuitive, but we need to go back to the idea of Avogadro to understand why this is what it is. And then we do the calculations: 3 moles per dm cubed, 2 moles per dm cubed squared, multiply, you get 108 m5 pentupled, and that's what it means. You can either write it as m5 or you can write it as mole pentuple divided by dm15. Either way, the answer should be correct. So this is what solubility products are all about, and and then they'll ask you to convert solubility product from molality to molarity. You might remember I spoke about it in the beginning of the video, and then they'll try to increase anonymity to make you do more work. I'll do separate calculations in the next video, but it was quite hard for me to try to explain, but I've just begun solubility product. And then it leads into partition coefficients, gas chromatography, this and that. It becomes a bit, all of these are unitary calculations depending on the common sense, and it leads into a very boring option of chemistry that I didn't take, which was chromatography. And I didn't take it because I didn't like chromatography, and I still don't. I had to put up with gas chromatography, HPLC, for quite a while in my first degree, and it's not something I enjoyed. I didn't. It was the diagrammatic representation depiction was quite enjoyable, but not the rest. So I'll take it from here. Thank you very much for watching the video. I'm glad you stuck with me all throughout, and I hope you'll be able to rewind and go back and forth the video to see and check your conceptual understanding of solubility, and then how you link it to solubility product in the framework of reaction kinetics. I hope you enjoyed it, and I hope you make the most of it and use it to bolster your performance in reaction kinetics of A levels. And thank you very much for watching this video. If you have any comments, please post them down below, and I'll try to answer your comments to the best of my ability. Thank you very much, and take care. Bye now.